Today I'd like to talk to you about this clock that I've designed. The idea behind it is that it shows the time like an analog clock in a sense, but instead of hands going around the face of the clock, there are LEDs arranged around it in a circle, and they light up different colors to show you the hours, the minutes, and the seconds. One of the reasons I decided to do this is that I've seen clocks before that had some interesting effects when they were showing the time like this, but I thought that it could be done more simply and more cheaply and with a better effect. And essentially, what I've done is uh, we'll show you some videos of this, as well as an hour and a minute and a second. It also has a sub-second display that runs around the face of the clock once per second, and it looks like it's actually pushing the second hand around. And I think that's a particularly nice effect. You can turn it off if you don't like it and you just want the clock to update each second. In fact, there are a few options that are accessed through the two buttons on the front. But fundamentally, I wanted to keep it a very simple design, easy to build, cheap, yet a useful clock that looks nice. It looks nice on the wall with nice effects. And so this design was published in Silicon Chip magazine. This is the article that you can see here. And as well as here's the introduction, shows you the front and the back of the clock, circuit diagram, the PCB design, front and back, some soldering tips, and the list of parts you need. And we also have a kit. So the kit comes with basically everything needed to build the clock. You just need to add a power supply, and it runs off 5 volts from USB or slightly higher. Maybe you're going up to 12 volts if you have a 12-volt supply. It has an onboard regulator, so it can run from a higher voltage. Uh, so the basic idea is that we have 60 light emitting diodes, LEDs, arranged in a circle around the face of the clock. And these are RGB LEDs, which means that each one actually consists of 3 separate LEDs sharing one lens. So there's a red, a green, and a blue LED. And by lighting them up, well, if you light the red LED, obviously it looks red. If you light the green, it looks green. If you light the blue, it looks blue. You can also light them in combination. So you could light red and green together would look yellow, blue and red would look purple, and if you do red, green, and blue all together, it would look white or some shade of white, depending on exactly how much current is going through each LED. So if there are 60 LEDs and each one contains 3 sub LEDs, that means 180 different devices to drive. And that's really the challenge with this clock: is how do you drive 180 LEDs without a massive chip in the middle with at least 200 pins? If you wanted to do it the obvious way, each LED has one pin to drive it. Say at the positive end, the negative end is connected to ground. Well, not only would you need a chip with 200 pins, so you could have 180 plus 20 spare for doing other things, you'd also need 180 resistors. So this would quickly become a very big job to put together. Instead, what I've done is I've used a trick that I've used before. I didn't invent this trick. It's called Charlie plexing, and it means that you can drive a large number of LEDs from far fewer pins than you might expect. And this takes advantage of the fact that LEDs will only light when current is flowing in one direction. So if you connect the voltage in the opposite direction across an LED, nothing happens. So if we look at the circuit now, um, you'll see that it's uh, these letters here. So we have the microcontroller has 20 pins, and of those pins, 2 are the power supply here, VDD, the positive, VSS negative. We have 3 others, one of which is used to get the time. The time comes from either a GPS or other satellite module, or from a Wi-Fi module via NTP. Um, so that one pin is dedicated to the timekeeping function. We have one pin here that actually does 3 different things. It senses the ambient light level using a light-dependent resistor, and that's so that when it's dark at night, the clock can dim itself so that it's not blasting you with light. And it also has 2 buttons connected to that same pin, and so you can press either button. It will sense that you've pressed that button. It can do things like change your time zone, change the brightness, so on. There's a few different functions. So that one pin is doing a lot. This pin here is a reset pin. Now, it is sometimes possible to use a reset pin for other purposes, but for the sake of simplicity, I've just pulled it up to 5 volts by this resistor, so the chip will just run normally. And that leaves us with, 15 pins, isn't it? So 20 minus 5, 15 pins to drive the LEDs. We also have a programming header, but most of the time you're not programming the chip, so those 2 pins here can be used to drive LEDs as well. So 15 pins, each of them has a 68 ohm resistor connected. and then I've labeled that the other end of each resistor A through O, and those are what connect to the LEDs. And so each there are various different ways to do it, but here we have 4 RGB LEDs in each group, so that's 4 times 3 is 12 elements. So there are 13 connections. We're taking advantage of the fact that these are common anode LEDs, which means internally the positive terminals are connected together. So they have 4 pins, 3 for the individual negative cathodes, and 1 for the combined anode. And I'm further combining 4 sets of anodes together to make 1 anode for each set of 12 LEDs, leaving us with 12 separate cathodes. So by using 13 pins here in this first group, LED 1 to LED 4, pins A through M, what we can do is if we want to light any set of LEDs in this group, we pull line A high, and we do that by pulling the RC0 pin 16 of IC1 high to 5 volts because it's a 5-volt supply. And then we pull some combination of B, C, D, E, F, G, H, I, J, K, L, and M low. And we do that by pulling these microcontroller pins low to ground to 0 volts. And of course, the software has full control over these pins. So we can drive any pin high and low that we want. And if we have, say, A high and I and J low, then LED 3 will light up cyan because it will be a mixture of green and blue. And we could also pulse width modulate either A or I and J, which means rapidly switching that pin on and off, and that would let us dim the LED. So that's it for this group 1 to 4. But what if you want to light 5 to 8? Well, in that case, instead of pulling A high, you pull B high, and then you'll notice that the letters here have shifted. So instead of B through M, it's C through N. But the point is, with B high, only one of these 4 LEDs can light. And if we look back at our first group here with B high, current cannot flow in this direction up. It can only flow down because it's an LED. So with B high, nothing will happen here with LED 1, regardless of whether A is high or low or floating. So by having each set of 12 anodes connected to, in turn, A, B, C, D, etc., so if we have 15 pins and these are groups of 4, that's 60 LEDs. So we can drive all 60 LEDs from these 15 pins. The limitation is you can only light LEDs in one group at any given time because only one of these should be high. If you drove, say, A and B high, well, then you wouldn't be able to light this red element of LED 1 because you'd have 5 volts at both ends and there'd be no current flowing through it. So you only drive one group high at a time. In practice, what we do with the clock, because we might want to light up to, say, 4 LEDs at once, we don't actually light them at once. We cycle through them very quickly, lighting one at a time. And because the human eye can't see that, it looks like all 4 are lit. So the software has an interrupt that runs rapidly several thousand times a second. And each time that interrupt routine is triggered, it switches to a different set of highs and lows to light a different LED in a different color. And that way we can, as the time moves around the clock face, we can choose colors, say red for hours, green for minutes, blue for seconds, and we can light the appropriate LEDs to show the time. And that's basically that's the majority of what goes into the clock. Now, obviously, the software to do this is fairly complicated. It does take advantage of some very nice features of this chip. It's a PIC 16F18146. The reason we chose this chip, it has enough pins. It has 20 pins. It's very inexpensive. I think it's about $1.50 US, possibly less if you buy them in large quantities. It's not particularly powerful in terms of CPU processing. It's an 8-bit chip that runs at about 20 megahertz, but we don't need to do a lot of number crunching in this application. We just need to get the time from the serial stream from this pin 4TX of Con3, decode it, and then do this multiplexing of the LEDs. That's the majority of what it has to do. One thing that helps us, if we look at, here's the data sheet. There's different variants. There's a 14 pin, we're not using that, we're using the 20 pin. But it does have this PWM module, which is a very flexible module. And what it means is that we can essentially program just about any pin on the chip to pulse on and off rapidly, and we can determine what percentage of the time it's high and what percentage is low, and therefore how bright the LED is. So we take advantage of this and just general digital IOs to do the clock face. Returning back to us, so there's our circuit. There are 2 additional LEDs I didn't mention, 61 and 62. They're optional, and that's for an AM PM indicator. You can see it here. And I just thought, well, one thing that an analog clock doesn't do is tell you if it's morning or afternoon. So we might as well add a couple of LEDs. We know the 24-hour time from GPS or from NTP. So we just use an additional multiplexing step to light one of these two, depending on whether it's morning or afternoon. We've talked about the LED, we've talked about the buttons that set time zones and such. We don't need to set the time because if it's coming from GPS, it's going to be accurate as long as we have the correct zone set. And you can do that using these switches in 15-minute increments. And then the rest is just a very basic power supply. So we have 5 to 12 volts DC coming in here into a 5 volt low dropout regulator. Now the output will be slightly less than 5 volts if the input is 5 volts, but in practice I haven't noticed any difference. If you feed 5 volts USB and it works fine, but it's probably slightly better to feed in something like 6 volts just to make sure you have a nice regulated 5 volt output to run the chip and hence the LEDs. And these extra components, Q1, ZD1, this resistor, all that does is just make sure that if you connect the voltage backwards, it's not going to damage anything. So basically, if you connect the voltage correctly, current will flow through the 100k resistor, pull up this gate, switch Q1 on, connecting the negative terminal to ground, and everything will work normally. If you connect it backwards, this will actually be negative, it will pull the gate low, and then Q1 can't switch on. And because this internal diode in Q1 will then be backwards, no current can flow between the negative terminal and ground, which will actually be positive at that point. And so the circuit simply won't run if it's reversed. ZD1 just makes sure that if you put, say, minus 20 volts on there, that it's not going to damage Q1, it's going to clamp it to 5.1 volts. So the circuit really couldn't get much simpler. We have about maybe 30 components total. And you can see from the PCB design that it's really only going to take like half an hour to solder all that stuff to the board. Most of the time in an assembly is simply fitting the 60 LEDs, which is it's not a difficult task. It's just a bit time consuming, partly because you want to make sure you do it properly. If you get short circuits between these pins, and if I zoom in, you'll see these pins and pads are pretty close together. You don't want to get short circuits because if you do, you're not going to be able to tell where very easily, because if LED 1 doesn't light, well, it could be because there's a short circuit between A and something, or B and something, or C and something, or D and something, and that could happen almost anywhere on the board. So the advice in the article is to solder a few LEDs. You've already put the chip on there and the resistors, apply power. The first thing the clock does is light each LED and turn white, and that very quickly lets you tell if there's a problem. So if everything's good, it will go LED 1 white, LED 2 white, so on all the way around the clock face. If anything is not white or doesn't light up, you know there's a problem, you switch it off. And if you've just added 5 LEDs, well, your problem is somewhere in those 5 LEDs. So you have a good look at the solder joints. Probably there's too much solder, and then you remove a bit of it and make sure that you've cleared the bridge and test it again. And it took me a few hours to assemble the prototype. Nothing too, and of course this was the first time I'd built. There was no instructions or anything, so it probably could go a bit quicker for somebody experienced who's presented with this known working design and just wants to build it. Here's the backup. Now, what you'll notice about this circuit board is it has what looks like quite an unusual design. It almost looks like an antenna or an inductor or something with these circular tracks, 15 circular tracks running around the outside. Now, the fact that there are 15 is not a coincidence. So what we decided to do was, because when you look at the circuit, you would say, well, how are you going to, there are going to be tracks going everywhere because you have G going here to these 4 LED anodes and to these 2 anodes, but you also have G going to this cathode and this cathode and this cathode and this cathode. How are you going to organize these connections? It would be a mess. Well, I didn't come up with this idea, Tim Blythman did, but he basically said, why don't you run 15 rings around the board near the LEDs and just wire up A, B, C, D, etc. to each ring in turn, and then all you have to do is have these radial tracks that connect to the LED pads, and we just put one wire in each of these radial tracks to connect it to one of the circular tracks, and that's all the connections taken care of. So it was just a matter of in the PCB design software creating these straight tracks and circular tracks, and then I just went around and just placed wires with the mouse, click, 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 after figuring out the pattern, and then all I had to do was run these tracks out from the resistors to some point on the periphery to each of the A, B, C, D, etc., and the job was basically finished. So the rest of the wiring, as you can see, is pretty simple, really. You just have your power coming up through here, through the regulator into the chip. There's the LDR, the buttons are over here. You have your GPS or NTP header and your programming header, and that's pretty much it. These pads here are just mechanical attachment points. You can see here I've soldered wires to them, and that's just so you can hang it on the wall, and so it sits nicely on the wall and doesn't actually scratch it or anything like that. And you can also see, if you have a look here, I've added this little subboard that's described separately. It's just a USB socket with some components and header, and it just provides a convenient way to plug USB in and get 5 volts into the board. Um, so that's pretty much it. We've showed you how the clock actually looks when it's working, and you can change the color scheme. That's just a quick, simple button press. Um, in fact, written on the back of the board, you can see here is are the instructions for what the buttons do. You can also do things like adjust the maximum brightness, the minimum brightness, and therefore how it relates to the LDR and the time zone. There's a daylight savings, a quick thing that most countries that have daylight savings, it's a 1 hour offset. So you can just add or subtract 1 hour. That way you don't have to do much when there's daylight savings change. Um, and otherwise the clock takes care of itself. And I've used here, this is a BZ121 module. It combines GPS, Baidu, GLONASS, and some other systems. So it's like an all-in-one satellite navigation system. But all we're extracting from it is the UTC time, uh, which once it's synchronized takes about 15 minutes after power up. If the time zone is correct, the way the clock goes, then it will just show the time, which will always be correct and accurate as long as you change it for daylight savings. So a nice, simple hardware design, I think. The software is fairly complicated, but luckily you don't have to worry about that. You just download it from our website. The source code is there. If you want to modify it, you can modify it. It uses Microchip's XC8 compiler. There's a free version, and that's all you need to compile this code because it's not particularly demanding. Oh, and I should mention one of the reasons I chose this 18146 chip. Not only is it cheap, it has a fair bit of memory as well. If we look at the data sheet, um, it has 28 kilobytes of flash memory, plus 256 bytes for data and 2K of RAM, which doesn't sound like a lot, but for an application like this, it's plenty. So that's why you don't need anything special in terms of the compiler. You don't need the code to run particularly fast or be particularly small. It's not doing a lot. It's just updating the clock, and it's all interrupt based anyway. So, and uses the PWM takes care of the dimming. So it's all pretty straightforward. But there's a lot of logic in there to get all the LEDs right, different modes and so on. But we provide a hex file that's the compiled code, and all you need to do is flash the chip. And in fact, if you buy a kit, the chip is already flashed, so you don't even have to do that. If you get a kit, all you need to do is solder the parts onto the board, wire up the GPS module, and we have instructions on how to do that. Connect power, and away the clock goes. So a nice project that has been reasonably popular. And I think it turned out well, pretty much exactly what I was hoping for. It's a digital clock that looks like an analog clock with a bit of an interesting effect to it, and that's customizable. So you'll always have the correct time on your wall. I hope you found that interesting. If you have any questions, you can email us. You can also read the magazine. So this is from the May 2025 issue of Silicon Chip Magazine, which is available as both a printed magazine and a PDF. And you can also read it online. And there's a lot more to it than just the clock. We also have articles on digital scent and taste, electronics trade show, Bluetooth modules, a precision electronics tutorial, a battery checker, which has also been a very popular project for us and is also available as a kit, tool safety timer, and my USB power adapter that in fact, I might as well show that since we've discussed it briefly. It's just a very simple little article here on this board. It's a cheap board. You can get a kit for a few dollars, and you have the choice of a few different USB sockets, and it's just an easy way to get USB power to a pair of pads to connect to something. Anyway, hope you found that interesting. Please check out Silicon Chip Magazine if you like this sort of thing. And we have usually most issues comes out every month. Most issues have at least 4 different projects in them, so plenty to build plus other articles that you might find interesting if you're into electronics. Thanks and have a great day.